Good morning, everyone. How are y'all doing today? Good? 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 Good. Cool. All right. Does anyone have any questions before we get started? Okay, cool. All right. So I just wanted to point out, especially as we start to get to these harder topics of now we have our organic reactions, especially getting into the substitution versus elimination, which is what we're starting today, is we tend to have much harder questions because it's just a more challenging topic. So things to keep in mind is that I have these weekly course schedules where one, it talks about everything that we talk about. It tells you what's happening in recitation. But at the bottom is where it is reminding you of where you can find additional practice problems. And so these are picking out ones that I think are best suited to the current content so that you can find relevant problems that are going to be ungraded to have extra practice. So obviously there is a lot listed there. I do not expect you to do all of them. I don't even expect you to do half of them. What I do expect you to do is try some of them to get the extra practice. So whether it be like the end of chapter problems, if you like the end of chapter problems, awesome, keep doing them. But remember that the solutions to the end of chapter problems are in this book. So it's in the separate book where you get the full work solutions. So if you don't want to look at a separate book, then maybe don't do the end of chapter problems. Instead, skip those and go right on to Achieve, because you have access to Achieve. So try the adaptive quiz. The benefit of the adaptive quiz is it's going to help identify certain topics that you might be struggling with. So if you're like, I don't know where to start, the adaptive quiz is a really good place to start. If you already know what it is you're struggling with and you want more targeted practice problems, but you don't want to do the end of chapter problems, then you might want to go to Dr. Baldwin's problem set, the study guide, or which the study guide is actually from my 2310 class, so it's not actually like a real study guide. It's just a summary of the content, or do some of these online practice problems. So these are online websites that link out to other published textbooks, other universities. That's for Minnesota University. So they have made their resources available online. So I went through and found the ones that I liked the most out of them, right? So all of these are found under the practice problem module. That's where you find all of these. So these are the online practice are linked over here. So the synthesis puzzle one is here for the synthesis puzzle, right? That's what it's referencing out. So that's where you can find those extra practice problems. So I just wanted to remind you that like that resource exists, and especially as we get into harder problems and harder topics, more practice is going to make sure that you perform better, especially coming into the next exam. So looking at our current week, we can see that the Tuesday recitation, so tomorrow's recitation, is going to be focusing on SM1 versus SN2, so the previous content, last week's content. Remember, Thursday recitation is canceled due to fall break. The university is closed, so there is nothing on Thursday or Friday. We also don't have class on Friday. So what we're doing today is looking at our elimination reactions. We're going to look at our alkene stability, degree of unsaturation, and going to get into the E2 reaction. Wednesday is going to be looking at E1 and starting to do some SM1 versus SN2, E1 versus E2. Your homework 5 is due on the Sunday of break. So hopefully you already started it and have been working on it for the last week and a half. But if not, it is due on Sunday. And then your 5th quiz is also going to be due on Sunday. So be aware of that. So if you are traveling for fall break, then reach out to me and I can give you an extension on this upcoming quiz. So if you need an extension for whatever, like I can give you an extension on the quiz. Just let me know and I'm happy to do that for you. right? And then again, here are relevant additional practice problems to look at. All right. Are there any questions about that? Okay. Are there any questions at all? Dope. Let's get into the second half of chapter 7, which is elimination reactions. So I don't know why the textbook does it this way, but our SN2 was all of chapter 6, and then SN1 was the first half of chapter 7. So now the second half of chapter 7 is eliminations. So our elimination reactions are the alternate pathway to substitution. They are in competition. So when we look at our alkyl bromide or haloalkane with sodium hydroxide, we can do an SN2 reaction and end up with an alcohol. So we can do substitution, where you go from one functional group to another functional group, and that is one reaction pathway. That is where the sodium hydroxide is acting as a nucleophile, where it's attacking the carbon. So that hydroxide acts as a nucleophile to attack the carbon. We're ending up with our new functional group on that alpha carbon. Alpha being the one that is directly connected to the leaving group. And then we use our Greek alphabet just to go out so that the next letter is beta. So it's alpha, beta, gamma, delta, epsilon, so on and so forth. So beta comes next. And what we're going to see is that when NaOH acts as a base, we're going to do a beta elimination, meaning that we're going to attack that beta hydrogen. We're going to attack a hydrogen. That makes our alkene, right? So NaOH can act as either nucleophile or a base. It is both a good base. We already said it was a good base, right? But it also has that negative charge. It's small. It also makes it a good nucleophile. So we're going to have to figure out, does it want to attack a carbon and do substitution? Or does it want to attack hydrogen and do elimination? And we're going to have this competition where we can get either reaction pathway. And we're going to have to try to predict which one is our major. Okay, so that's ultimately our goal, is going to be building up to that, is knowing when we're doing substitution, when are we doing an elimination, predicting our products, predicting our mechanisms. That's where we're going. Before we start talking about elimination, though, we have to look at our alkenes. And we have to talk about the stability of our alkenes and the properties of our alkenes first. So we have to look at the product properties before we can really look at how we make them. So this is technically chapter 11. I don't know why. But things to keep in mind are trans are going to be more stable than cis. That's because of the lack of sterics when you are trans, right? When you are cis or Z and your large groups are close together, that's going to increase your steric hindrance. That increases the energy, decreases stability, right? So you're more reactive, less stable. We're also going to see that the more substituted you are, the more stable you are. So this is just like with our carbocations, because we're going to see that hyperconjugation, that delocalization of electron density through space, is going to stabilize our alkenes. It's going to help spread out the electron density for us. So we see that if you are monosubstituted, you have one non-hydrogen attached to your alkene, monosubstituted. That is the least stable, right? So that's all the way to the left, is the monosubstituted. Our disubstituteds come next. So we see that substitution is the greater factor here, that we're going to consider substitution first and then sterics. So now in the disubstituteds, we see that 1,1 disubstituted is next because that has the most sterics, with the two groups being really close together, attached to the same carbon, as compared to our 1,2 disubstituted, where they're on opposite carbons, or on either side of the double bond. But again, cis is less stable than trans. Then we get our tri-substituted as the next most stable, where again, we're gonna see that Z is less stable than E. And then we'll consider our tetra-substituted, and again, Z will be less stable than E. So the number of substituents is the greater stabilizing factor. So you first identify how many substituents you have and try to categorize them first, and then look at sterics. So substituents first, then sterics when predicting your alkene stability. Look at your substituents first, the number of substituents first. That's the more stabilizing factor, then sterics. So our alkenes, we know that they are a locked conformation, right? That as soon as you rotate one of the p orbitals, that breaks your pi bond. Pi bond, the only way to get a pi bond is from those parallel unhybridized p orbitals. That makes your pi bond. As soon as you rotate one and it becomes perpendicular, there's no pi bond because they're not parallel anymore. When you are at extremely high temperatures, that is very, very hot. Remember, water boils at 100. So this is like 400 degrees Celsius. This is like oils are on fire at this point. Like this is very, very, very hot. Extremely high temperatures, you can force your cis to become trans. You can force your alkenes to become the more stable. You can convert between them. So this is known as thermal isomerization. It's when you have extremely high temperatures, you can force your pi bond to break so that there is no pi bond. So here you're imagining you are cis and you are locked. We get that really high heat. That high heat breaks the pi bond. So it rotates out. So that now it's essentially unlocked. There's no pi bond at that point. So now we have the option of when we rotate, do we rotate back up or do we rotate down? You can rotate in either direction, and you're going to rotate to whichever one gets more stable, whichever one gives you the more stable alkene. And so then that's what we're going to see here, is what it's trying to show, is that deuterium, we see that it flips, so that it now becomes trans, it gets locked again, and it is more stable. So this is not common. Getting to those temperatures is very, very, very difficult. Like, yeah, you need extremely hot ovens, very hot, very hard. But if you give it enough energy, you can force it to go to the more stable alkene, right? But in general, it's really hard to make it unlock. So when we think about the amount of energy associated with these alkenes, we can also think about the strength of our bonds, not just the carbon-carbon bonds, but also our carbon-hydrogen bonds. So those vinyl, CH, which remember vinylic, means that you are on the double bond. You are directly attached to it. So our vinylic CH, that hydrogen attached to that alkene directly attached to the double bond is going to be stronger than just a normal alkyl CH. Trying to write the word ankle. That's weird. Alkyl. So just a normal alkane CH. And it's because of the fact that this is an sp2 hybridized orbital versus sp3. If you are sp2, you have more s character, less p character. So now your orbital is going to be more spherical. You are closer to the nucleus. So that means that you're going to get a shorter bond because you're going to have these electrons more attracted to the nucleus of the carbon. It's going to make it harder to remove that hydrogen. So we will never remove the hydrogen on a double bond. We're not going to do it. We're not going to take it. It is too strong of a bond. The only time that we will is to make our alkynes. So it'll be one specific case. And it's exactly this. This will be the only time you can ever take a vinylic CH, is where you have it antiperiplanar, which is what we're going to call this. It's when it's perpendicular, exactly opposite of a leaving group, and it is your beta hydrogen. This is the only time. This will be an E2 reaction to make an alkyne. This is the exception, the only time you'll be able to take a hydrogen directly on a double bond. Otherwise, don't do it. It's not an acid. We're not going to take it. Another property associated with our alkynes, not alkynes, well, it is alkynes, but with our pi bonds, is degree of unsaturation. So our degree of unsaturation tells us how many pi bonds or rings there are. So each pi bond or ring equals one unsaturation. So one pi bond is one unsaturation. One ring is also one unsaturation. Each unsaturation represents the loss of two hydrogens. So our general formula for our alkanes, just straight chain alkanes, was that CnH2n plus 2. That was the general molecular formula for an alkane. When you get to an alkene, assuming the alkene has only one pi bond, you lose two hydrogens. So now your formula is CnH2n because you lost two hydrogens. When you get to your alkyne, now you are CnH2n minus 2 because each time we're losing, okay, that's weird, we're losing two hydrogens. Because each time you're adding one unsaturation. Each unsaturation represents the loss of two hydrogens. Our formula for degree of unsaturation is this, where you have 2 times the number of carbons plus 2. This is the maximum number of hydrogens in a saturated alkane. Well, yeah. So this is the number of hydrogens for the alkane, right? That's the 2n plus 2. 2 times the number of carbon plus 2. That's looking at the maximum number of hydrogens possible. Then you're going to add in however many nitrogens you have. Each nitrogen will add an additional hydrogen. So we have 2 times the number of carbons plus 2, plus the number of nitrogens, because each nitrogen adds 1 hydrogen. Then we're going to subtract the number of hydrogen or hydrogen equivalents, so our monovalent things. So we're looking at, all right, so what are the maximum number of hydrogens possible minus how many actually exist? How many do I see? And then we're going to divide by 2. You divide by 2 because each unsaturation is from, so one unsaturation is 2 hydrogens. So we're going to divide by 2 because there are 2 hydrogens lost per pi bond or ring per unsaturation. Bless you. So it is the maximum number possible minus how many exist divided by 2. That is your degree of unsaturation. It tells you how many pi bonds or rings you have to have. This formula, I will not require you to memorize. If you do memorize it, it will help you because it tells you what structural features must be present. It tells you about what your product would have to look like or a starting material would have to look like. So it's beneficial, but every problem I give you, you'll be able to solve without knowing the degree of unsaturation. I will expect you to be able to calculate degree of unsaturations by looking at the number of hydrogens that you have and then comparing it to your alkane. So you still have to have that CN2N plus 2. That formula still has to be memorized. And so then you can compare to the maximum to then know how many unsaturations you have to have, or by counting the number of pi bonds and counting the number of rings tells you the number of unsaturations. But I don't expect you to have this formula memorized. I think in lab they do require it, so knowing it now can help you. But yeah, I hope that expectation was clear, that you technically don't have to have it memorized for this class, but it'll be very helpful if you do. All right, so let's look at this being applied. So I have C3H8. So that means I'm going to do, all right, 2 times the number of carbons, which is 3, plus 2. Then I'm going to say plus the number of nitrogens, which is 0, minus the number of hydrogens, which is 8. So that's our nitrogens. That's the hydrogens. That's carbon. Minus the number of halogens, which is 0. And then all of that divided by 2. So this works out to be, so 2 times 3 is 6, plus 2 is 8. 8 minus 8 is 0. 0 over 2 is 0. So that means if you are C3H8, you have 0 unsaturations. So the only way to make that molecule exist is here, is to just be propane. There are 0 rings or pi bonds. There are no unsaturations. When you add in that nitrogen, we now have C3H9N. I see that I have 2 times 3, that's the number of carbons, plus 2, plus my 1 nitrogen, minus 9, I still end up with 0 over 2. So when you have this bond replaced, like there originally was just a hydrogen here, when I put a nitrogen there, I have to add on this other hydrogen. So when I add a nitrogen, it adds a hydrogen. That's why you had to add in the number of nitrogens. It increased the total number of hydrogens by 1. So I still have 0 unsaturations. I have 0 rings, 0 pi bonds for that structure. There are a lot of variations in that structure. That is a primary amine, but it could have been a secondary amine, right? Could have had a secondary amine, or I could have had a tertiary amine. My molecular formula doesn't tell me my connectivity, but I do get the indication on pi bonds and rings. So this is the primary amine because your nitrogen is attached to only one carbon. Your secondary amine because it is attached to 2 carbons. And then your tertiary amine is because that nitrogen is attached to 3 carbons. You still have 9 total hydrogens every time you do it. If you are now C3H7N, I can compare to my maximum, and I see that I've lost 2 hydrogens. So that alone tells me I had to have 1 unsaturation. That I expect you to be able to do without the formula. But if I use the formula, if I have this memorized, it becomes easier because then I just plug everything into the formula. It's 2 times 3 is 6, plus 2 is 8, plus 1 is 9, minus the 7 that I see. That is 2 over 2 is 1. So that tells me that I either have 1 ring or 1 pi bond. Because I have 1 unsaturation. And each unsaturation is either 1 pi bond or 1 ring. I can't have both. Unless I have 2 unsaturations, in which case then I could have 1 ring and 1 pi bond, because then I have to add up to a total of 2. Cool? Does that make sense? Degree of unsaturation? Expectations are clear? Yeah. Wait, say that again? I'm sorry. Yeah. So the +1, I assume, is they don't have that 2, right? In their numerator. Is their numerator just 2 times carbon plus nitrogen minus H minus X? Yeah, what they did was they pulled out this component. And so they said 2 divided by 2 is 1. So they did 2 times carbon plus nitrogen minus hydrogen minus halogens plus 1 instead of dividing anything by 2. So what's up? Yeah, so you still have to, okay, yeah, that's fair, because that is how algebra works, I'm sorry. Yes, you are right. So this, what they're doing, is they're just pulling out that component, is what I mean to say, is they're pulling it out to represent that you have 2 fractions, so it still needs to keep that same denominator. So it is still that divided by 2. Thank you. So it's that divided by 2. The +1 is just because it pulls that out. So I personally don't like that they do that formula because I think it's more confusing as to where that formula comes from. And it's because it's an algebraic manipulation of my original maximum number of hydrogens, the 2n plus 2, the thing you already had to have memorized. Just adding a nitrogen minus hydrogen minus halogen gets you the same formula. Cool. Any other questions? Okay. So in lab, they pulled out that 2 to get 2 times your carbon plus nitrogen minus H minus X over 2 plus 1. But that's where it came from. Okay. All right. So now that we know about our product stability, we recognize that it's a type of unsaturation. We know that in order to get out of that locked conformation, we need extremely high temperatures, which means we're not going to worry about that isomerization really at any of our normal temperatures that we operate at. Now we're ready to do our elimination reaction. Now we're actually ready to make our alkenes, ready to make those pi bonds. So our elimination reactions are going to eliminate a leaving group by removing a beta hydrogen, hydrogen next door, to make pi bonds. That is your elimination. All of our elimination reactions will have a base that will deprotonate. So it is like your nucleophile, but we are attacking a hydrogen. It is still the electron-rich thing, but it's going to attack a hydrogen. So we still have to have a base. We still have to have something that's electron-rich. Then we need to have an electrophile that has a beta hydrogen. That is our substrate. The substrate is the thing that has the leaving group. Then I need to have a leaving group, just like with substitution. It'll be the same trends as substitution. You still need to have that good leaving group. A leaving group is still required for elimination. And then the additional thing that we're going to see is that our product is going to be gaining a pi bond. So you're going to get at least +1. So if you're making the alkene, when we're making alkyne, you can actually make 2 pi bonds. So we're going to be increasing our number of pi bonds in the product. But we still have the same requirements as a substitution reaction, right? Because every substitution reaction had our nucleophile, our substrate, the thing with the leaving group, the electrophile, and a leaving group. So these are the same reactant requirements, same starting material requirements as substitution. That's our challenge. That's where our challenge is coming from, is that they're going to look similar, but lead to different products. Start out looking the same, end in different places. So our general reaction is going to be where you have a base. That is the nucleophile or Bronsted base. I'm going to put nucleophile in parentheses because it's not going to attack a carbon. It could if it did substitution, but we're going to consider it a base because it's going to attack a hydrogen. Then I need to have my electrophile, the thing that is going to act as the Bronsted acid. And then that's going to make my alkene. Then my byproducts are now leaving group left. That's the same as what I saw before. But the difference is that I now have that hydrogen connected to the base. Because I'm getting a new pi bond between my alpha and beta carbons. So I have to lose that beta hydrogen. So that's alpha, that's beta. That's alpha, that's beta. So that's the general reaction, is base plus your electrophile, the acid, the substrate, is going to now make the alkene, where you have leaving group left as a byproduct, and the base took the hydrogen. It took the beta hydrogen. Just like with substitution, we're going to have 2 elimination mechanisms. So we're going to have E1 and E2. And just like with substitution, the number does not tell you the number of steps. The number tells you the number of reactants in the rate determining step. So what that means is that E2 is one step because both compounds are involved in the slow step. So E2, that bimolecular, is because there are two reagents in the rate determining step. E2 is one step. It is concerted. It will generally compete with SN2. E1 is similar to SN1, where it is going to be two steps. E1, two steps. It is stepwise. So it's that unimolecular because the one tells me that there is one reagent in my rate determining step. So it is two steps. So what we're going to see is with E2, it is leaving group leaves as base deprotonates, just like how SN2 was leaving group leaves as nucleophile attacks. Now it's leaving group leaves as base deprotonates. E1 is like SN1, where SN1 was leaving group leaves then nucleophile attacks. Now it's leaving group leaves then base deprotonates is our E1. That tells me the E1 is going to make carbocation intermediates, just like SM1 did. Our general mechanism for E2 is going to be where you see that base. With your electrophile, your base is going to take the hydrogen. It has to happen all in one step. So the base attacks the beta hydrogen. We're going to break that hydrogen-carbon bond and give those electrons to make that carbon-carbon double bond. So the electrons fall over because hydrogen can only make one bond, so we got to put the electron somewhere. The electrons are going to make the pi bond. Then that's now making too many bonds to this carbon, because remember that hydrogen's still there. So that is going to now make 5 bonds to carbon. I can't have 5 bonds to carbon. That's not possible on the surface of the Earth. So we need to now have another arrow going away, kicking out the leaving group so that we don't violate carbon's octet. So E2 is always going to have these 3 curved arrows at once. Base attacks the hydrogen-carbon bond makes the double bond, and then we kick out the leaving group. You get all 3 arrows each time. So this is concerted, so it's all one step, where I now see that alkene product, that protonated base, and the leaving group left. That is my E2. E2, one step. Because both my base and my substrate are connected. They're reacting together all in one step. There are 2 things in the one step. So E2 for the 2 molecules reacting together. E1 is going to look like SN1, where it's going to be leaving group leaves, then base deprotonates. So we're going to see step 1 is leaving group leaves. That's going to make our carbocation intermediate. Now, in step 2, my base can deprotonate. Why can't I draw a curved arrow? There we go. So in step 2, now base deprotonates to make the alkene. Cool. So instead of attacking that carbocation directly, if it did, that would be SN1. Instead of attacking the carbocation, we're going to attack next door. We're going to attack the hydrogen to make the double bond. That's the difference between the SN1 and E1, or SN2 and E2. Substitution attacks the carbon. Elimination attacks the hydrogen next door. Oh, sorry, still some people writing. So next, we're going to look at the detail parts of the mechanism, just like how we did with SN2 and SN1, where we were talking about all the special considerations. We're going to do that, and we're going to start with E2, and then we'll do E1. We ready? Okay. All right, so for our E2 reaction, this is where we have that general rate equation where our rate depends both on the substrate, our electrophile, and our base. You need both in one step. So the rate equation has both substrate and base involved in it because E2, two molecules. Our potential energy diagram is going to show the one step because it happens all in one go. So if my starting materials are that base and my electrophile, I still see this energy of activation barrier because there's one energy of activation barrier for each step. That is my slow step because it's the only step I have. So there's going to be that relatively tall barrier. And then our products are the alkene plus our protonated base plus the leaving group that left. So when we go to draw our transition state, assuming that it is exothermic, that means that we are assuming an early transition state because we are matching the one that is given. I can now draw my potential energy, or not my potential energy, I can draw my transition state. My transition state it's going to be where I have a partial bond being formed between the base and the hydrogen, partial bond being broken between that hydrogen and that carbon, a partial double bond being formed between the carbons, and a partial bond being broken between the carbon and the leaving group. And because I made that a propane, we'll put the methyl there. Okay. And this is what our transition state is going to look like, where that hydrogen and that leaving group are 180 degrees from each other. They need to be on opposite sides. We'll talk about why in like 2 minutes. But you got to make sure you're drawing them on opposite sides. All right, so if we're assuming this exothermic early transition state, I can also now assign partial charges and predict long and short bonds, right? That's that Hammond postulate. Okay, so what needs to have a partial charge? Yeah. Yeah, the base. So we look most like the thing that we are closest in energy to. So I need to look most like my starting material. The only thing that's charged in the starting material is the base. So that means that base has to have a partial negative charge, right? Everything else is neutral in the starting material. If I didn't know that I need an early transition state, then I wouldn't be able to assign the partial charges because I wouldn't know. Or you could assign both partial negative there and there because it'd be right because you wouldn't know what you're supposed to look like. But because I gave you an exothermic, I can now assign my partial charges. I can also assign long and short bonds. So the base hydrogen bond, is that going to be long or short? Long. Why? Because it doesn't exist yet. Remember, the long bonds are the ones that don't exist yet in whatever thing you're closest in energy to. So that one is long. All right, how about that carbon hydrogen bond? Short, because it does exist. The hydrogen is still there. It's implicit, but it still exists. How about that carbon-carbon double bond? Long, because it doesn't exist yet. How about my carbon leaving group bond? Short, because it does exist. If we were endothermic, all of these would have flipped. Our long and short labels flip, and the partial negative would have been over here. If you were endothermic, that's a positive. Partial negative. Because now you would have to look more like the products, right? So it's because we're assuming exothermic, that's what's telling us that our products need to look like that. All right. Any questions about predicting that transition state for E2? Okay. So we're going to affect our rate by looking at our base strength, our substrate structure, and our leaving group ability. So essentially, our E2 is going to be affected in similar ways as SN2, which makes sense because you need both the base and the electrophile in the rate determining step. So both are going to impact our rates. Before we get to rates, though, I want to look at this stereochemistry assignment. The fact that I told you that your hydrogen and your leaving group have to be 180 degrees from each other. That is the consideration of being anti-periplanar. So anti-periplanar is saying that you are going to be opposite on the same plane. So the same plane, but opposite side. So anti being opposite. I don't actually know what the prefix peri means, but planar meaning like plane. So it's telling me that my leaving group and my hydrogen must be 180 degrees from each other. That's what anti-periplanar means. So when I look at my substrate, if I were to draw a Newman projection, and I look at it like I'm looking down the left-hand side. I have 3 hydrogens on the front carbon. I have a leaving group going straight up on the back. My methyl is down to the right. Hydrogen is down to the left. So anti-periplanar is showing that I have this anti-alignment, that my leaving group and my hydrogen are 180 degrees from each other. In order to do E2, you must be anti-periplanar. Just like how SN2 said you must do backside attack, E2 must be anti-periplanar. It will not happen. You will have no reaction if you cannot be anti-periplanar. The reason why is because of orbitals. So why? Because I need to access that sigma star. I have to do it all in one step, so I got to get to that sigma star. So what I'm going to look at is this will lead to my sigma bond, right? So if I have an sp3 hybridized orbital plus the p orbital of that chlorine, that's what I see here, then that is going to lead to my sigma bond, that bonding molecular orbital, where you get all of that electron density there, and you get the little thing there, right? That is your sigma bond, where you get that big orbital overlap in the middle, back orbital in the little side, right? That is your sigma. Simultaneously, you also get the sigma star. Remember that you can't have one without the other. Two things in equals two things out. So if I have that sp3 plus a p, that equals a sigma plus a sigma star. Two things in, two things out. The sigma star always exists simultaneously, just empty, and then once you put an electron in, that breaks the bond. So once these become out of phase, so that now the ones that are near each other are not in phase with each other, the shaded versus unshaded, they're mismatched, they are not compatible. That pushes the electron density away from each other because they repel, because they're not compatible. So I get this is now my sigma star. So that sigma star exists on top of the sigma just as it did, or on top of the same bond, just as it did with the sigma. But now what we're going to see is that we actually have that big, then little, little, big. That is our sigma star. This is that sigma star. So now where that electron density is accessible, where that sigma star is accessible, because here's where I have all of this electron density. There are electrons existing here. Electrons exist on top of all of this. So my electrons from my base, or from that parallel hydrogen, are going to be repelled here. Where they can access is on this backside, where I only have a little bit of electron density right here, but I have a big region of where I can accept electrons to break the bond. And that's what we're going to see. So that this is my sigma orbital, so that this would be like that, would be my sigma, and actually there. And my base, those electrons from that base are coming in, are attacking that hydrogen. They are taking the hydrogen, and then the electrons from that sigma orbital are falling into the sigma star. It has to be parallel for those electrons to lean over. Remember that our electrons can only travel between head-on or side-on. That's the only way that our electrons can move. So the electrons from that sigma bond can go into that sigma star, break that sigma star, break that sigma bond, kick out our leaving group, forming our carbon-carbon double bond. So the electrons from that CH, sigma orbital, are going to move over into the sigma star of that carbon leaving group, where the accessible side is on the back side, 180 degrees from the leaving group. So your hydrogen has to be 180 degrees from your leaving group, because that's where the accessible sigma star is. That's where the accessible part of your sigma star is located, right? So this is the only way to do E2. You must have antiperiplanar. If you do not have antiperiplanar, you do not have E2. All right, have a wonderful day.